All right, today I will first talk about a nice application of Clifford's theorem, which we have seen in the last video. Then I will discuss about the restriction of a representation to a normal subgroup of order 2. Let's recall that in the last video we were talking about the restrictions, we were talking about a restriction on a normal subgroup. So when the subgroup has index 2, then we can even get some more precise information. So which we will do in this video. So before that, let's see a nice application of Clifford's theorem. So let G be a finite group. Let G be a finite group, and assume that all irreducible characters of G has all irreducible characters of G have order p to the power r, where r is a non-negative integer, and we fix a prime p. P is a fixed prime such that, so P is a fixed prime such that P is a fixed prime such that so we start with the group G, finite group G. Let P be a prime such that all irreducible characters of G, all of them have order p to the power r. Then what we will show is there exists a normal subgroup of G, which is abelian. Let me first write abelian thing. There exists an abelian normal subgroup N of G such that P does not divide order of N, but the quotient group has order, this has order some p to the power L. Okay. So again, let me repeat the statement. So if we have a prime such that all irreducible characters of G have, again, here it will be dimension, characters have dimension. So all the irreducible characters have dimension, some order of P. Remember, trivial character is also included here. That's why one-dimensional characters are also included here. That's why we allowed R to be greater or equal to 0. If this is the case, then there is a normal subgroup of G such whose order is co-prime to P, but the index of the normal subgroup is some power of P. Okay. So the situation is basically any such that P does not divide order of N, but however the once we take the quotient by that subgroup, the quotient group has, or for that quotient group, P is the only prime that divides the quotient group. So P does not divide order of N, but so the situations are completely opposite. Here P does not divide order of N. So the prime divisors or order of N are completely different from P. However, when it comes to G modulo N, then no prime other than P can divide the order of G modulo N. And as in particular, we will show in this situation, of course, G cannot be simple. unless G is isomorphic to Z modulo Pz. Isomorphic to Z modulo Pz. This is what we will first show. So how to show this? We will our method for proving this will be the most typical one, which we frequently do in finite group theory, that is induction. So we will we would like to do induction on the order of G. So in order to run an induction argument on the order of G, what we have to do is we first have to reduce the order, right? Only then we will be able to use induction hypothesis. Now, in order to reduce the order of G, there are two standard ways. The first way is to pass through factors, okay? Factor by some non-trivial subgroups. So that then the order becomes less than the order of G, and we can use the induction hypothesis. But there is, in this case, that approach does not seem to be of some help, because suppose you pass through some, suppose you want to pass through some factor group, but then what may not happen that in that factor. So here you have the addition, you have the here the main information is given by this, that is all irreducible characters have a degree some power of p. Since in general we do not have a way to reduce the characters of G, irreducible characters of G, to the irreducible characters of a factor group, because the kernel of these irreducible characters, the intersection of the kernel of these irreducible characters may not contain any normal may not contain any non-trivial normal subgroup of G. So therefore, in general, we have no way to reduce the characters of G to the characters of a suitable factor group. So hence we have to give up. So give up if yeah, we have to give up our approach of passing through factor groups. So here we rather look for here we rather take the other approach, that is, instead of factor group, we will try to get a proper subgroup, non-trivial proper subgroup of G. Okay. But then the question that you can ask, that why can one even expect, or even at least have some feeling that this approach will not be going to wane as like the factor one. So this is a pertinent question, that for factor groups we see that we don't have any hope. So why would one be hopeful to uh, uh, to run induction by picking up subgroups in G? So the reason for which we have some hope is precisely we have our Clifford's theorem that we have seen earlier. So let me just explain. So suppose H is a normal, H is a normal subgroup of G. H is any sub. Let's take H is any subgroup of G, and let's assume that phi 1, phi 2, phi L are all sorry, psi 1, psi 2, psi L are all irreducible characters of H. Irreducible characters of H. Then for any irreducible character of chi of G, we can write the restriction of chi. We can write restriction of chi as a sum like this: d1 d1 Hmm, D. Okay, okay, no problem. Let me just make a change. So let me just make a change. Okay, so let's yeah. So well, let me make a change. That's better. So what I'm going to say is, let me just formulate once again. So the reason for which this approach of considering subgroups might lead us to the correct thing is precisely the following. So let if psi is an irreducible character of H, then there exists an irreducible character chi of G such that res psi is non-zero, right? This is what we know. So what does that mean? That means that the irreducible representation which has chi as its character, that irreducible representation is contained in the restriction of the representation corresponding to chi, right? So once that is there, then it is very easy to see using Clifford's theorem that restriction of chi to H, if we write that, let's say in the following form, that d, let's say d1 psi 1 plus dl psi l, dl psi l, where psi 1 up to psi l are distinct irreducible characters of H, but I don't claim they are all, are some distinct irreducible character of H. I don't claim they are all. So if this is so, then once we evaluate both the sides at the identity point, we get the dimension of chi is same as uh, first of all dimension of chi1 up to dimension of psi 1, dimension of psi 2, and the dimension of psi l. The Clifford's theorem says that they are all same. They are all same. So basically, and this psi is one of them, right? Because according to our assumption, that is a irreducible character, which so it's a character such that the representation which has this as a character is contained in the representation, in the restriction of the representation which has chi as the character. So therefore, thus what we get is dimension of psi times the something like so let's say some d1 up to dl. In fact, from Clifford's theorem, we see that they are also di equal to dj, but let's not. We don't need to use that right now. So basically, what it shows that dimension of psi divides dimension of chi. Okay, and since dimension of chi is a power of p, so thus that holds for dimension of psi as well. So the upshot is, what we have seen is, if we take any subgroup H of G, then any reducible representation of that subgroup has also dimension power of p. Okay, so if the subgroup is proper, then we see that since the hypothesis also holds for that subgroup, so therefore we can use the induction argument on that subgroup. Okay, so that shows that the idea of the idea of looking at subgroups, that indeed has some merit. So it is not as hopeless as looking at factor groups. So with this observation, so since this shows that we have some hope here, so let's do it. Okay, So how should we start? First our approach should be looking at some age, some appropriate age, some suitable age, because again you see, it is true that for any age all that we have observed here follows, but the problem is, so suppose you choose any proper subgroup age and then run the induction argument on that, then you will get an n such that p does not divide order of n, but the index of n in h has order some power of p, but then the main difficulty will be to get n, main difficulty would be to get n normally in G, which is we are supposed to show. So I mean, just the normal subgroup of some H may not be normal in the whole of G. So therefore, we have to choose H also in a careful manner. So that's what we will do now. So recall that the formula for this formula, which we have seen, which we have used several times earlier. So we retain the usual notation. So n1 up to n cap the dimension of all irreducible representations of G. So some of these ni's must be, some of these ni's can be 1. So what we do is we first gather those ni's in this sum which are 1. So first we just take the sum of those ones, and then we'll just we will just we'll just take the sum of other ni's. Okay, let's write other ni's. So then what is the order here? What is the sum of what is, so what is here, what we have is the number of ones appearing here is same as the number of one-dimensional representations, and for a group G the number of one-dimensional representations is same as the order of its factor group modulo the commutator subgroup, because every one-dimensional representation of G comes as a one-dimensional lift of one-dimensional representation of this. Okay. Now let's see the following, that as we said that well, so if anything lives here, so if G is abelian, then nothing is here, right? Because all of them are already so all ni's are 1. So then we just see that if G is abelian, then this statement is already true. Okay, then this statement is already true. Trivial, in fact, because for any abelian group, we have proved that corresponding to every divisor of the order of the group, there is a subgroup of that, and that has to be, and that is automatically normal. So for G abelian, there is nothing to do. So we shall assume throughout, we assume that G is non-abelian. Assume G is non-abelian. So once we assume that G is non-abelian, now let's see that that means at least there is some Ni here, and that Ni, due to the dimension theorem, that Ni also, because the degree, the order of any reducible representation also divides the dimension, the dimension of an irreducible representation divides order of G. So Ni being some positive power of P has to be some positive power of P divides order of G as well. Okay. Now, I mean, this holds for any Ni in this sum. So what it shows, so what we have is this part is divisible by P, because any term in this, any summand here is a positive power of P. So this part, so P divides this, and then P divides order of G as well. Therefore, P has to divide the order of this abelian group. Okay, order of this abelian group. So now it is quite clear that if since P divides this order of this abelian group, since P divides the order of this abelian group, so therefore there will be a subgroup here having index P, and once we pull that back to G using this quotient map, we get, pulling back by G, by this we get there is a normal subgroup, because under homomorphism, under onto homomorphism, normal subgroup of image becomes a normal subgroup of G containing the kernel, that is here containing G prime. And so there exists, so since the subgroup here as index 2, so once we pull it back in G, it is easy to see that that also has index 2. So thus we get a normal subgroup of G such that order of order index of index is P. Okay, index is P. All right. So now what we do is, this is since index is P, so H has to be, H cannot be whole of G, and hence we apply this general observation which holds for any subgroup H. So from that, so therefore H has all irreducible characters of H have all dimension some power of P, so that we can apply this induction hypothesis on the order of induction hypothesis, and we get a normal subgroup N of H such that this happens. Let me just write. There is, from induction hypothesis, there exists a normal subgroup of H. I repeat, normal subgroup of H such that P does not divide normal sub, so P does not divide N, but on the other hand, this has order for some L, P to the power L, sorry, H. I'm sorry, here I should have written H. Okay. Now we claim is, this is the N that will work for our G. So claim is N is normal in G. Well, I think I have I also have this condition, need abelian normal. So here there exists abelian N, abelian normal. So N is abelian, and we already have this. So we just have to now show that this is also some P to the power L prime for some L, L prime that are equal to 0. Okay. Okay. So we have to establish these two things. So showing this is actually easy. I'll just leave it to you. This has so observe that this is P, and N is contained inside H such that H modulo N is P to the power L for some L, and H modulo N is P to the power L. Okay. So from that, I leave you to check that. It is in fact P to the power L. So it's indeed P to, so from this and that we will get this. I leave you to check. Okay. Because we have in the two steps. First we can partition H as cosets of N, and then again as cosets of H, G is also partitioned. So therefore, taking some products, you will see that N can be partitioned the number of ways, the number of cosets of G in N is basically the product of something like this, the product of objects like this and that. Okay, so I leave that part to you. So I will just now establish this, because this is the important thing. So first, for that let's observe that let G be a G such that order of G is not divisible by P. So a group element whose order is co-prime to P. Then first we claim that, then we will see that G belongs to H. Why? That is quite easy to see. If G, so we look for GH, which is in G modulo H. Okay, and so the order of GH in the quotient group, that has to divide the order of G. Okay, now what is the order of that? If G does, if this does not happen, then GH cannot be H, but this is a cyclic group of order P, so therefore this has order P, and thus P divides order of G as well, which challenges our assumption. So that means G belongs to H. Then in the next step, we say that the similar argument will show that G belongs to N as well. Why so? Because again, that we look for the coset Gn. So if G does not belong to N, then the order of this coset in H modulo, now G belongs to H, in H modulo N, it will be some positive power of P, but that divides again the order of G, right? That divides the order of G. So therefore this is a positive power of P, which is dividing order of G. So again P is dividing order of G, which is again a challenge. So G belongs to N. Thus what we have shown is every group element whose order is co-prime to P is contained inside N. And now that shows that, and from this it is quite clear that why for any X in G, X and X inverse is going to be whole of N. Because if you take any elements from N, so if yeah, so just a minute, let me just complete the argument. So first of all, what we have just proved is every element of G whose order is co-prime to P lies in N, and any element of G has order must have order co-prime to P, because the P does not divide the order of N. So therefore, thus you can see N contains precisely all elements whose order are co-prime to P. And from that, now it is clear that for any X in G, X and X inverse is N, because once we have an element from N, and once we conjugate that by X, after conjugation the order does not change. So therefore, once we conjugate that, then the order still is co-prime to P, hence it has to be in N. All right. So thus we have proved this. We have proved this. Now we will just complete this part, and that's also quite easy. So how to complete this part? So now again let me just remind you that we have established this already. So we want to show that G cannot be simple, so unless G is this. So suppose G is simple. If G is simple, then N, which is a normal subgroup of G, N can be either trivial or whole of G. Okay, N can be whole of G. Okay, so if N is whole of G, then that means G is abelian. Okay, so we have assumed that G is simple. So simple and abelian, then G must be Z modulo Pz. So this is for this case. If n is just trivial, so if n is trivial, that means G is a P group from here. So it has center. So the center of the P group is non-trivial. But again, from simplicity, the center has to be whole of G. So that means G is again abelian. And once G is abelian, G has to be isomorphic. Since it is simple, it has to be Z modulo Pz. So that's an easy. So from here to here is actually very easy. All right. So this is a nice application of Clifford's theorem, because if Clifford's theorem would not be there, then we would not be able to run the induction argument through the subgroups of G. Okay, Clifford's theorem make it possible actually that once we consider a appropriate subgroup of G, then this property in the hypothesis, in view of Clifford's theorem, so in view of this property that you see in the hypothesis, in view of Clifford's theorem, you can see that also holds for H as well. All right, so now we shall come to the next part, the second part of this video. So recall that in the last video we were talking about restrictions of yeah, just a minute. I think here yeah, I just forgot to mention that the G that we have to choose has to be normal, because otherwise one cannot use Clifford's theorem. I might have missed that in the beginning anyway. So basically, since we could not pass through factor groups, we rather look for some suitable normal subgroup, and then Clifford's theorem indeed made this condition happen for H as well. Okay, so let's come to the next, as I said, that the next part of this video. So when we restrict a representation to a subgroup or to a normal subgroup, then at most what we can say that all the subrepresentations, that irreducible subrepresentations of all the irreducible subrepresentations, at least I mean, by irreducibility we rule out the non-trivial thing. We rule out the trivial thing. So all irreducible subrepresentations have the same degree and they occur exactly same number of times. This is a very important theorem, and then which indeed limits the possibility for a restricted irreducible character of G. Now what we are going to see is, if the subgroup has index 2 in addition to the normality, of course index 2 implies normality, then we can say something more. I mean, even we have some more precise information. So let's see that here. So the first thing that we will see here, so assume that index of H in G is now 2, okay, and V rho is an irreducible representation of G whose character is chi, and let so first we so let H be a W be an H invariant subspace of V. It's an H invariant subspace of V, and assume that this is irreducible as well. That means it doesn't have any further H invariant subspace which is different from the trivial one and W. Okay, so because, well, let me just again say in a different way that what we are doing. So first we restrict rho to H, so that becomes a representation of H. Then we choose then we have taken an irreducible sub-representation of that. Okay, so then what are the possibilities? The first possibility is either, so the first possibility is W could be V as well, because when you restrict that to V, restrict that to H, so V as a representation, V, so the representation of H on V, that could also happen to be irreducible. So the first possibility is that this is irreducible. If not, then what can we see? If not, then the restricted character what can we say about that? So if psi1 up to psi l are irreducible characters of distinct irreducible characters of H, so where psi1 up to psi l all irreducible characters of H, distinct irreducible characters. If we write this like this, then what we must have is the following. Then what we must have is d1 square up to dl square is less or equal to the index. So what does that mean? So index here is just 2. Now you see the sum of square is less than or equal to 2. So when is that possible? That possible only when one of them is 1, or there are two term di which are 1 1 and rest 0. Okay, so exactly 1, so yeah, so exactly 1 di is 1, rest of them are 0. That means that the restricted character is just equals to some irreducible character of H, which, so that means this becomes irreducible, which is already taken care of in the first case, right? So therefore in the second case it cannot happen that exactly 1 di is 1 and rest are 0. Rather what should happen is there will be di and dj for I not equal to j, which are 1 and 0 elsewhere. So what does that mean? That means the restricted character so is the sum of two different irreducible characters of H. So thus we have exactly two possibilities. Possibility one is the restrict. So one. So if chi is an irreducible character of G, then the restriction of chi to H, either it becomes irreducible or it becomes the sum of two distinct irreducible characters. Okay, so we will finish in some minutes. So basically now let's observe that for any group G, suppose rho is a representation of G on V, finite group, and at the same time let lambda be a one-dimensional representation. So in that case we can just take it to be the multiplicative group of C. So it's a one-dimensional representation of C. Then we get another representation of the same dimension of rho, so which is defined as we define it by lambda rho. So a typical G goes to lambda G times rho G. It's easy to see that because if lambda G1 G2 is rho G1 G2, since lambda being a one-dimensional representation is a homomorphism, so lambda G1 G2 will be lambda G1 times lambda G2, so you can push lambda G2 inside. So therefore for any one-dimensional representation, so any representation being multiplied by a one-dimensional representation is also a representation of the same dimension, And it is also easy to see that rho is irreducible implies lambda rho is irreducible. Okay, this is a very general observation. Now we shall use that to a very particular context, that suppose H is a normal subgroup of index 2. Okay, then G modulo H is being isomorphic to Z mod 2Z. Okay, so so therefore we have exactly two characters of G modulo H. The first one is trivial, the other one is sending everything to, sending every non-identity element here to -1. So once we take the lift of that character to G modulo H, so if that is our character, or representation, if we take the lift of that using this quotient map, then we get the following. So if lambda be, lambda be the map in this context, which sends let this be generated by x, so which sends x to -1. Okay, so once we lift that to here, we get the following character of the following one-dimensional representation of a G, such that for so lambda rho, so the lambda hat of H is identically 1, and if G does not belong to H, then G when it projects down to here, it becomes it comes down to H, it comes to X. So therefore this becomes -1 for all G does not belonging to H. Okay, so this is the lift of the character lambda hat. So henceforth, for simplicity in notation, we will call it this one by lambda. We will call this by lambda and simply forget about what we have said, because we would like to avoid too many notations. So thus for us, lambda is the one dimension, thus from now onwards for us, to us, lambda is the following one-dimensional representation of G, which sends every element of H to 1 identically and other elsewhere -1. So this is basically the analog of sign homomorphism of Sn. So now for this lambda, and then for any representation rho, we will consider this lambda rho. Now the question is, what has this to do with the restriction of rho to H? So with that we will finish that. So as I said, let gamma be the character of rho. Let gamma be the character of rho. So first what we write is we consider restriction of rho to H. Okay, so suppose this is irreducible. Suppose this is irreducible, then what does that mean? So if this is irreducible, then you see, then here we can never have equality, right? Because this side has to be 1. So recall that here equality occurs if and only if the character of this representation is such that it vanishes identically outside H. So if and only if condition, therefore here what we can just say that there exists G in G modulo H such that chi G is not equal to 0. Okay, this is what we can say. What about the converse of this? The converse of this, if this happens, then that means the here equality cannot occur. So if equality cannot occur here, so the only choice for the left hand side to be just 1, and left hand side is 1 means exactly 1 dy is 1 and rest are 0. So therefore this is irreducible. So the converse is also quite easy. So what we have seen is these two statements are in fact equivalent. Now we will connect this to this lambda rho. So well, so let me again just make a common observation that for any lambda and any rho, so if this is the case, then what is the character of this lambda rho? It is simply, you can see that the character of lambda rho is simply lambda, the value of the character at the point g is lambda g times chi g, right? Okay, so lambda g times chi g. So basically it is, in simple terms, lambda chi is going to be the character of lambda rho. Okay, so now let's just simply see that for that g for which this happens, then what is the value of lambda chi at the point g? Lambda chi at the point g, this is simply lambda g times chi g. Since g is outside h, so it has to be chi g. Okay, and chi g is non-zero, so that is certainly not equal to chi g. So therefore what we have just seen is the character lambda chi and chi, they are not same. Okay, so far we have just proved one direction. Now we will prove the other direction. Suppose lambda chi not equal to chi, so that means there would be some g such that lambda chi g, which is minus chi g, and minus chi g is not equal to chi g. But you see that if well, again let me repeat. So now we assume this, so that means there exists a g in g such that lambda chi g is not equal to chi g. Okay, so what are the possibilities for this? If g lies in h, then certainly this cannot happen. So therefore this g has to be outside h. Once this is outside h, this just becomes minus chi g. Okay, and that immediately forces that this has to be non-zero, because if yeah, so if lambda chi g not equal to chi g, then certainly if lambda chi g not equal to chi g, then chi g certainly cannot be 0. Okay, because the value of lambda chi g is plus minus chi g. So thus we get a point. From this assumption we see that g has to be outside g. So thus we get a small g outside h, and for that g this fellow is non-zero. So this is precisely what we have here. So thus we have the following, these three things equivalent, that is a restricted character is irreducible if and only if it is non-vanishing, it is not vanishing at least at one point outside h, or in other words, this two, or in equivalently these two characters lambda x, lambda chi and chi will be different. Okay, okay, I will stop. Before I stop, I just let me make a remark here. So try to understand in this case that when lambda is precisely this, so for any representation rho and any representation rho, and so this context, this is the context when you have a normal subgroup of index 2. So first of all, both the representations, when you restrict both of them to h, what you are going to get is exactly same. So these are two distinct irreducible representations of g whose restriction. So and both of them are, so if one of row is irreducible, then this is irreducible as well, but their restriction on H are equal. Okay, so now therefore we were, so on the restriction on H are equal, we want to know whether we want to know whether they are equal everywhere on G or not. So that is answered by this equivalence. So if lambda rho, well, so again, I'm sorry, just what I wanted to talk about, not the representation as well, mainly the character. So let me just again repeat. So when we have a normal subgroup of order index 2, and then suppose for any representation row, if we take this lambda, then we have row lambda, their characters are chi and lambda chi. So the restriction of chi and lambda chi on H are equal. Okay, they're equal. So the question is whether, so their restrictions on H are equal, but the question is whether they are equal everywhere on G or not. So this equivalence now shows that they will be equal. They will be equal if and only if the restriction of chi is not irreducible. Okay, so the restriction of chi is irreducible if and only these two characters are different. Okay, so with that I will stop. I think things are clear. Let's stop.